Good day, everybody. And for my presentation today, I would be talking about the recent progress of solar cells. And in particular, I'm going to be looking at the perovskite type of solar cells. So moving on, for my journal list, I have selected three journals. And the first one is regulating the surface termination for efficient inverted perovskite solar cells with greater than 23% efficiency. For the second journal, I have chosen ultrafast laser annealing of perovskite films for efficient perovskite solar cells. And finally, for my third journal, I'll be looking at a journal called the Efficient and Stable Radialston Popper Perovskite Solar Cell with Tailored Interlayer Molecular Interaction. Now, for my first journal, regulating surface termination for efficient inverted perovskite solar cells with greater than 23% efficiency. The executive summary is as follows. One of the fundamental factors that limits a solar cell's efficiency is the existence of direct recombination of electron hole. As such, it is important to continue research on finding ways to reduce this phenomenon. This paper successfully presented their research and findings on how they use a novel bifunctional molecule piperazinium iodide that contain both electron donors R2NH and acceptors R2NH2+ on the same six-membered ring to passivate and reduce the surface defects on perovskite solar cells, basically to aid its stability via released surface residual stress and efficiency improvements via reduced non-radiative recombination losses and lower open circuit voltage. Additionally, no doubt they achieved results of 22.75% is still lower than the theoretical 30% max limit of solar cell defined by the Shockley-Quasar SQ limit. The research has conducted has paved ways on further improvement opportunities. Now, the research methodology that I'm going to be sharing with you next is Li F et al. They approach this research by looking at one of the fundamental issues of solar cells that limits its efficiency, i.e., the presence of surface defects and the need to passivate them, reduce electron hole recombination, i.e. the non-radiative recombination. Additionally, they also looked at the various passivation molecules already tried by other researchers and found that most of them can only passivate either the positively or negatively charged defects on the surface. Now, there were only a few that can passivate both the Pb2 plus and halide ions trapped on the perovskite surface, an example being the quaternary ammonium halides. Continuing on the research methodology, they thus decided to come up with a novel bifunctional molecule piperazinium iodide that contains the R2NH and R2NH2 plus group on the same six-membered ring with an in-plane dipole that is capable of functioning as an electron donor and an electron acceptor to react with different surface terminating groups. Now, the synthesized crystal structure looks like this over here on the screen, the figure 1 here. So basically, you can see that the H bond over here, it is clearly indicated in blue here. And then the lead nitrogen bond is over here. Now, as for the results in the discussion from the research conducted by Lee and P et al., the resulting PI-treated perovskite solar cell surface had a reduction in residual stress of the film surface. Additionally, a more N-type characteristic film was produced, and this facilitates more and easier charge transfer. Now, from both the above improvements, there was suppressed non-radiative recombination loss in the V open circuit loss of 0.33 volt with a very low delta V3 of 60.13 millivolts. Now, a certified independent lab measurement obtained a power conversion efficiency of 22.75%, a current density at short circuit of 24.684 milliamp per centimeter square, and a V open circuit of 1.164 volts and a fill factor of 79.16%, which is a very high fill factor. Now, continuing on further on the results and the discussion, here you can see the various graphs, from the characterization analysis that they had done. So clear performance improvements are seen on the PI, the piperazinium iodide, versus the PDI, which is the piperazinium diiodide passivated, versus the reference perovskite solar cell, as clearly seen here on figure 2. Right, these are the various graphs you can see, and the average PCE showed a marked improvement of about 2.59%. Right, so that's over here. So if you look at this, 22.88 versus the value obtained by the reference 19.67, the average it comes to about 2.59% increase. Now, also the VOC improved to 1.17 volt from 1.06 volt due to the PI passivation. Now, continuing further on the results here, the photoluminance spectra as well as the time-resolved photoluminescence plots of the perovskite films, you can see that the steady-state charts indicated on chart 3A over here. Now, it indicated that the PI passivated PVSC had a highest, about 5x improvement, followed by the PDI passivated about 3x when compared to the reference PVSC. Now, this infers the non-radiative recombination losses has been vastly alleviated owing to the passivated surfaces. Now, figure 3b over here, you would notice that the TRPL decay curves demonstrates a longer recombination delay or time for the PI passivated versus the PD passivated versus the reference PVSC, right? So this is the PI passivated. So it shows a 1948 nanosecond recombination delay or time, which is the much longer versus the 1461 for the PDI versus the 305 nanoseconds for the reference PVSC cell. Now, additionally, on the results and discussion, on these box plots, you can notice that the PCE box plot for the PI, for the various bills that were built for this entire experiment, they were much higher here. And additionally, for the V open circuit, it's also much higher versus the reference and the PDI. And for the current density, it is similar, I would say, to the reference, no doubt. But then for the fill factor, you would see it is definitely much higher. So over here in this table 1, it summarizes the various information that I just presented to you in a summary in this table. Now, moving on to my second journal, the ultrafast laser annealing of perovskite films for efficient perovskite solar cells, I would like to bring you to the executive summary first. Amongst others, a fundamental factor that affects a perovskite solar cell's performance is the quality of the film's crystal. Now, the lower the photovoltaic performance, it is caused by films with smaller grain sizes since they have higher density of trap states and lower carrier mobility, leading to an undesirable higher carrier recombination. Naturally, to improve the PVSC's film crystal, thermal annealing is used to induce larger grain sizes that would ultimately improve the photovoltaic performance. Now, this paper presents their research and findings on a novel linear laser annealing technique to provide an ultra-fast controlled crystallization process within a few seconds using a linear laser of a high intensity and a fast scanning speed while keeping the substrate temperature lower or as low as the ambient temperature. Now, moving on to the research methodology. To tackle the problem of small grain sizes in the perovskite film, thermal annealing is needed so that larger grain sizes can be produced, and this would lead to an improvement in the photovoltaic performance. Unfortunately, typical annealing conditions compromises the growth of the PVSC's grains as it's difficult to control the crystallization and it's a time and energy consuming process, which is also incompatible with low temperature fabrication needs. And it can be a bottleneck for mass production of PVSCs. As such, a novel annealing approach is much desired to overcome all these limitations. Now, continuing on my research methodology, UP et al. Presents their research and findings of utilizing a novel high-intensity linear lasing technique, annealing technique of various wavelengths and power modulation to aid an ultra-fast yet controlled crystallization process while ensuring the substrate temperature is kept low. They conducted their research on methyl ammonium lead iodide, MaPbI3, and cesium PbI 3005, FaPbI3 0.95, and MaPbBr3 0.05 mixed perovskite films. Thus, for their research to identify the optimum laser spot scanning annealing conditions to produce the better performing PVSC, they carried out various experiments by using 3 different laser wavelengths of 405 nanometers, 450 nanometers, and 660 nanometers. At the same time, they also varied the laser power to 110 milliwatts, to 130 milliwatts, to 150 milliwatts, and finally 170 milliwatts, while keeping the wavelength the same. So, okay, they repeated this for the various wavelength. And then they also varied the scanning speed from 10 millimeter per minute to 25 millimeter per minute to 50 millimeter per minute and 100 millimeter per minute, while keeping now the set power the same. All right. In their quest to provide a more manufacturing friendly type of setup in terms of speed of production and cost, they also successfully did additional builds using a linear type of laser beam to provide a faster laser annealing process of perovskite films. Now for the results and discussion, over here you could see the SEM analysis as seen here on figure 1. Right, so it was found that the largest average grain size of 476 nanometers over here was produced when the laser use had a 450 nanometer wavelength, and the smallest average grain size of 206 nanometers over here was produced when the perovskite solar cell was annealed with a standard hot plate method. Now moving on to further results. As seen here on this chart, the absorption ratio chart, you would notice here on figure 2 that the as deposited and the laser annealed perovskite film, the absorption rates are much different. So from the magnitude of the absorption, the light absorption of the PVSC film, which is the red line here, is much higher than the as deposited film at any wavelength here in the black line. So now additionally, pay attention to this peak over here, right? Absorption ratio here peaks around 465 nanometers, this green arrow here. And this infers that by using a laser wavelength of 465 nanometers to carry out the annealing, the thermal annealing, it may present an opportunity for further optimization whereby the scanning speed could perhaps be increased slightly, thereby reducing the overall production time. So By the way, a UV visible is to have a clearer understanding of the laser annealing effects, and the absorption ratio indicates the perovskite grains can absorb more energy. All right. So from the various laser annealing parameters adjusted for the bills, the best film produced was with predominantly, with larger average grain sizes, higher PCE, the power conversion efficiency, and good stability was with the laser of 450 nanometer wavelength at 25 millimeter per minute scan speed and at a power of 150 milliwatts. Now, additionally, the substrate temperature on the surface was only momentarily at maximum 100 degrees Celsius, where the laser beam was traversing, while the back surface, when analyzed with a fluke thermometer, right, the back surface remained at the room temperature, which makes it ideal for production of low temperature substrate PVSCs, such as plastics. Typically, a hot plate thermal annealing technique requires tens of minutes, and would definitely cause the entire substrate to heat up, which is not favorable for low temperature substrates. Now, moving on to further results from this table over here, which summarizes the various categorization and data, the the voltage open circuit, the current density J here at short circuit, the fill factor, and the power conversion efficiency, and of course the champion power conversion efficiency among the various bills. All right. So from the various analysis done, summarized here, you could see that definitely the champion among all is when the laser was at 450 nanometer wavelength, the laser output was 150 milliwatts, and the laser scanning speed was at 25 millimeter per minute. Now, for the third journal, the efficient and stable Ruddleston Popper perovskite solar cell with tailored interlayer molecular interaction. Here's my executive summary. Owing to unique properties of 2D, two-dimensional Ruddleston Popper, 2DRP in short, perovskites, it has attracted much attention for use in perovskite solar cells. So when compared to their three-dimensional 3D relative, the 2D Ruddleston Popper, 2DRP, possesses improved moisture resistance, greatly enhanced photostability and thermal stability, ultra-low self-doping, preventing unintentional defects, and significantly reducing ion mobility. So this paper is an experimental and theoretical combo study on the bulky ammonium layer, the interlayer interaction among adjacent 2DRP perovskite sheets, as its interaction controls the assembly of 2DRP layered perovskite segments and the charge transport across the segments. Thus, by modifying the interlayer molecular interaction among the 2DRP layered perovskite segments, the paper investigates its impact on the efficiency and the stability of 2DRP PVSCs. Moving on to the research methodology. To improve the intrinsic properties of the 2DRP perovskites, the researchers looked at the bulky ammonium RNH3 layer's unique degree of freedom as it influences the 2DRP perovskites in several ways. Firstly, the 3D perovskite is truncated, providing a lower dielectric constant layer around the MX sheets, providing quantum and dielectric confinement and promoting a large exciton binding energy. Secondly, it interacts electrostatically with the MX sheets, causing distortion of the perovskite framework and affects the electronic structure of the 2DRP perovskites. Thirdly, its crystal growth dynamics is affected and thus the morphology and the quality of the perovskite films as well. Though much research has been done with various bulky ammoniums such as pentylethylamine, phenylethylamine PEA, butylamine BA, and others to continuously enhance the efficiency of the 2DRP PSVCs rarely has the interlayer interaction amongst the 2D reactions has been investigated. Thus, this research focuses on this area. For their research, 2-methyl thioethylamine hydrochloride was chosen and found that sulfur to sulfur bond strengthened this interlayer molecular interaction. Here you can see the yellow dots here are the sulfur bonds, sulfur and sulfur here. Using the first principle density functional theory DFT calculations, it revealed that the SS interactions with MTEA tails provided enhanced interlayer binding energy and the charge density overlap as seen in figure 1 here. Due to the S interaction, the S-S interaction, a smooth, dense, and pinhole-free 2DRP perovskite film with low trap state density was formed, and it allowed an efficient charge transfer process. For the results and discussion, the MTEA-based 2DRP with 5 layers N5 films exhibited a strong outer plane preferential crystal growth with respect to the context over the BA-based films. Now, a high-performance 2DRP PVSC with PCE as high as 18.06 was achieved, surpassing the PCE of the BA-based device of 15.94%. The strengthened interlayer molecular interaction significantly improved the environmental and thermal stability of the 2DRP perovskite films. Most importantly, the MTEA-based 2DRP PSC still maintained over 85% of their initial efficiency under continuous light stress at the maximum power point MPP of 1000 hours. Now moving on to additional results. As seen from the SCM images here in figure 2, you could see that the high quality 2DRP works perovskites can be achieved. The 2DRP MTEA2 MAN-N-1 PBN I3N+1 perovskite film exhibit platelet structures. These are platelet structures here you could see from N equals 1 to 4 with relatively high roughness. They are pretty rough here, N1, 2, 3, and 4. And pinholes too, many pinholes as well, indicating the obvious Rudolphin proper phase layered structure. Whereas for the N greater than 4, which is the films tend to be smoother here for 5 and 6 with fewer pinholes, wherein for N equals 5, the film had a compact and flat with no pinholes. However, for N equals to 6, the number of pinholes had increased as seen here in the SEM image. Now over here are the AFM analysis conducted on figure 3. So you could notice that the relatively high roughness and pinholes is still noticeable here in N4 and N3 as well. Now when the for N5 onwards, basically for N5 there were less pinholes, and however, but again for N equals 6, the pinholes had increased. All right. Now this is the current density chart for the 2DRP MTEA2 MA4 PB5 I16 improved. Basically, the current density greatly improved versus the BA perovskite, right? So the red line here is for the MTEA build. It is clearly much better than the BA. All right, and this is because it has improved the JSC. The JSC is the current density of the short circuit, which is a consequence to the highly vertical oriented and high quality 2DRP perovskite films with the low trap density and a high charge mobility induced by the sulfur to sulfur interaction. Now looking further From the 60 devices of the 2DRP of both the BA type and the MTEA type perovskite, you know, we analyzed the current density. And in figure 5 here, you could see that, you know, the incident current, photon to current efficiency matches the J, which is the current density of the short circuit. So now the device in this case averages a PCE of 17.35% for the MTEA version, whereas 14.51% for the BA version here. So you could see that over here. Now, additionally, you could see that the PCE had improved. Now, among all of these three, journals or literatures that I've studied, this is the overall comparison that I would like to share. Now, the paper on regulating the surface termination, the first paper, regulating surface termination for efficient inverted perovskite solar cells with greater than 23% efficiency, they used a novel bifunctional molecule, piperazanium iodide, that contained both the electron donors R2NH and acceptors R2NH2+, on the same six-membered ring to passivate and reduce the surface defects on the perovskite solar cells, basically to aid its stability via released surface residual stress and efficiency improvements via reduced non-radiative recombination losses and lower open circuit voltage. Now, for the paper number 2 on the ultra-fast laser annealing of perovskite films for efficient perovskite solar cells, presented research and findings on a novel linear laser annealing technique to provide an ultra-fast and controlled crystallization process within a few seconds using a linear laser of a high intensity and of a high scanning speed while keeping the substrate temperature low. Now, for the third journal, basically the efficient and stable Ruddleston perovskite solar cell with tailored interlayer molecular interaction presented an experimental and theoretical combo study on the bulky ammonium layer, which is the layer interaction among adjacent 2DRP perovskite sheets. As its interaction controls its assembly of the 2DRP layered perovskite segments and the charge transport across the segments. They prove that by modifying the interlayer molecular interaction among the 2DRP layered perovskite segments, they were able to investigate its impact on the efficiency and stability of 2DRP PVSCs. Now, for my overall conclusion, so basically for the various three papers, right? So for the first one, right, basically the conclusion here is it is a very effective surface defect passivation technique using a bifunctional molecule containing both the R2NH2 plus and R2NH groups on a six-membered ring to improve both the efficiency and stability of inverted PVSCs. The PI molecule with an R2NH electron donor and an R2NH2 plus electron acceptor forms a dipole to reduce residual stress and suppress non-radiative recombination losses in the perovskites to boost the efficiency of the inverted PCSs to a very high value of 23.37%. It was actually 22.75% certified by an external lab, and a reduced VOC deficit of 0.3 volts. This work paves a new way for using rationally designed molecular passivators to reduce the surface defects of perovskite films and further improve the efficiency and stability of derived PVSCs. Now, for the second paper regarding the ultra-fast laser annealing technique, the conclusion here is an ultra-fast laser annealing approach for the preparation of both the MAPBI3 and mixed perovskite films at room temperature was done. Perovskite films were crystallized under high-intensity laser in a few seconds, and the average grain size was controlled by tuning the laser wavelength, scanning speed, and output power. So under optimum conditions, high-quality perovskite films with good crystallinity and preferred orientation and low density of defects were successfully fabricated. The temperature gradient can act as a driving force for the crystallization of perovskite grains and lead to larger grain sizes than the conventional thermal annealing method. A linear laser beam has been successfully used to achieve faster annealing process in a large area, highly compatible with the mass production of PVSCs. Now, for the third paper, in conclusion, right, in this work, we have it shows that we have shown that the interactions among the organic tails of the ammonia molecules play an important role in constructing efficient intercalcated 2-DRP hybrid perovskites by having the sulfur to sulfur interaction as reported. So the 2-DRP perovskite films with strong out-of-plane preferential growth reduced by the sulfur-to-sulfur interaction typically enable efficient charge transport, effective charge separation, and also, my apologies. So moreover, the strengthened interlayer molecule interaction yields a 2-DRP perovskite stable to temperatures well above 85 degrees Celsius, rendering a 2-DRP perovskite particularly interesting family of materials. So the discovery of the 2-DRP perovskites, provides an alternative framework, for us to further do the research on this. Now, as a summary, I feel that the paper on the ultrafast laser annealing of perovskite films for efficient perovskite solar cells by UP et al. Is perhaps the most interesting and novel among the three, as it addresses one of the most fundamental challenges faced by solar cells, i.e. the quality of the film crystal. UP et al. Has clearly demonstrated proper research and avenue to further their work to enhance the production of perovskite solar cells by enabling a cheap and fast method to effectively anneal the films to produce larger grain sizes that would directly aid in PVSC performance improvements. Additionally, their analysis on the light absorption indicated that it peaks around 465 nanometers, inferring that by using a laser wavelength of 465 nanometer to do the annealing, it may present an opportunity to do further optimization, whereby the scanning speed could perhaps be increased slightly. Additionally, the spot and linear laser annealing of a high and fast scanning speed technique can provide an ultra-fast and controlled crystallization process within a few seconds, while keeping the substrate temperature low, certainly paves way to the use of low temperature for where production uses low temperature substrates. So anyway, these are my appendixes. So the flow chart here shows that whether or not the improved perovskite solar cell has, for the first journal, has it met the higher PSC. If it's not, it goes through the various steps here, and then these are the various manufacturing steps taken, and then after which, once it is completed, it'll be going through a full characterization analysis. Now, during the various characterization analysis, if it has met and improved or higher PCE, then we can say we have successfully produced a PVSC with higher PCE using a passivated termination. All right. Now, the subsequent, this is the actual, schematic or structure of the piperazanium iodide passivated perovskite solar cell, as shown here in Figure 1, where it consists of the indium tin oxide, glass, polybisphol, vinyl 2,4,6-trimethylphenylamine, PTAA, perovskite, piperazanium iodide, ultra-thin fullerene C60, which is a type of a graphene, and a bathocupurine BCP. Now, this is the flow chart of my second literature, which is the ultra-fast laser annealing. So did the improved annealing produce a PVSC with higher PCE? And did the film have larger average grain sizes? If it is no, then we go through the literature search to find out what are the techniques done before, from terms of a laser. And then we identify the the annealing parameters that could further improve the PC and, to provide larger grain sizes. After which, we purchase the standard material required and we produce the PVSC. And subsequently, as shared earlier, we have the three three approaches that we use, three different wavelengths of the laser, and then varying the laser power, and also varying the scanning speed, right? And of course, for a control build, we just anneal it, using a standard annealing technique using a hot plate in the glove box. All right, subsequently, full characterization analysis is done, after which, we'll analyze, from the data obtained whether the laser annealed PVSC is able to achieve much higher PCE, and the film has higher average grain sizes. All right. So for my references, these are the various references. And thank you very much to Dr. Shamsul Nasrik for his continuous guidance provided. Thank you very much and have a good day.